Okay, well, welcome to week 4, everyone. We're well on our way to finishing this course. Today we're going to be kind of going over some more specific things about, how we might design things, and, we're going to give you some insight into 3D printing. So, yeah, just keep in mind, I'm going to do a lot of yapping today. It's a little bit less interactive than other weeks, but all of this information is very, at least I think it's very valuable to you for, both the final in this class, but also just as a designer in general. So I know this is going to be a lot of information. I'm giving you the warning now. But if you can do your best to absorb some of it, I think it'll be beneficial for you in the future. But yeah, let's just hop right into it. Okay, so I'm going to introduce your final project again in this class. Just kind of a reminder that this thing does exist. Again, it's just kind of a free range project. You can kind of do whatever you want, as long as, obviously you make something in Fusion. It's not something that we've done in class already. And, you kind of adhere to at least 5 design features, which, if you've been kind of following along with some of these demos, 5 design features is very, very achievable. But the last component is that it must be designed with manufacturability in mind. So once you finish your final and you submit it to me, you will have the option of having your design 3D printed. So I know a lot of us are maybe not near Purdue right now, including myself. But when we all come back in the fall, I'll bring my 3D printer back to school or back to Purdue, and I'll 3D print all the finals from the summer, and then you can, pick it up and stuff. So that's the end goal for this class. It's really awesome, at least to me, to kind of have something tangible after I do some kind of thing, some kind of project. So, we hope that you enjoy it as much as I do. I love printing all your finals and seeing what you come up with. But someone asked if we can 3D print in Bechtel. I'm pretty sure you can, yes. There's a 3D printing club at Purdue and stuff like that. I'll talk about that later today. But, I have my own printer, and for this class, I print all the finals, like, personally. So, yeah. You've probably seen this slide before. Again, these are past finals from other sessions. Many of these finals that you're looking at today or in these photos have a lot more than 5 design features. So, again, 5 is just the minimum, but, we definitely encourage you to exceed that and kind of see how far you can go with it. So these were pretty awesome. Again, if you don't make something like similar to these, don't sweat it, right? This is, a pretty fast-paced course, and, we don't expect you to create like some insanity, but someone always does, and it really impresses us. So again, it's a 5 design feature minimum. I know people might be taking summer classes or they might be interning, so I get that time may not be on your side. So yeah, I understand. You have the requirements. We encourage you to exceed them, but if you're busy, we understand as well. Okay, so now getting into the meat of today, we're going to be focusing on designing with manufacturing in mind, right? So The shortened like acronym that a lot of people like to use is DFM, or Design for Manufacturing. So we're going to be talking mainly about 3D printing, but we're going to kind of give you an overall idea of what you should be thinking about. Okay, so let me move this real quick. Okay, so we typically kind of categorize the manufacturing process in two different ways. So the first category is what we typically call subtractive manufacturing. So it's when you have some kind of material to start with, and then you take some tool, and then using some kind of process, you remove material from the original, block or whatever geometry you had before. You remove material until you have your final product, right? So you can see from left to right, at the beginning, we're kind of working with this square or this block. This tool comes in, cuts away at it until we have our final product. And this is a very common practice for many different manufacturing methods. So here are just a few, if the slide wants to go. Okay, here it is. Right, so all of these are subtractive processes, right? You're removing material, right? When you're drilling a hole, you're clearing the material out of where it was with some kind of drill bit or something like that. Milling is very similar, but you can do a little bit more complex stuff, right? You're not just doing holes, you're doing like outer geometry, stuff like that. Turning is when you have a spinning workpiece and some kind of tool that moves along it to create nice round parts. And then there's other stuff like routing and grinding and stuff like that. But in essence, all of these are removing material away from, your base, right? You remove material, stuff goes away, and you have your final geometry at the end. In many cases, you can do it with very, very hard materials, right? You can see in these photos here, there's usually some kind of metal involved. It doesn't have to be, but especially with milling and turning, you're typically using some kind of metal, right? Aluminum, steel, brass, all of those things are typically machined in some kind of subtractive manner to get a part. And although these parts are really awesome, they're really strong, these machines to make these parts can get pretty expensive, right? A really, really high quality milling machine can cost, upwards of $1 million. And, I don't know about you, I personally don't really have $1 million burning a hole in my pocket for a really nice milling machine. So a lot of these manufacturing techniques or manufacturing methods are kind of inaccessible to most people. Obviously, we're at Purdue right now, so there is a machine shop, and you can get things machined. But when you graduate or go on your way, these methods kind of become a little bit less accessible. You can hire people to machine parts for you, but it can get pretty expensive pretty quickly. So they're great. They're very precise typically, but they're pretty expensive for most of these. Drilling, if you have a drill or whatever, that's cheaper. But milling and stuff is pretty expensive. So we're not really going to talk about this too much today, but keep in mind that these different processes exist. And when you design things, you should be designing with, the tool that you have in mind when it comes to making it. So in this case, we're mainly going to be talking about additive manufacturing today. But yeah. So additive manufacturing is kind of the reverse of subtractive manufacturing, right? It's all kind of in the name. You kind of start with a blank slate, and then you have some kind of tool that deposits a material until you have your final product, right? In this case, this diagram kind of represents kind of some kind of 3D printing process, right? There's this, build plate here, you deposit a material, you keep doing it in layers and layers until you have your final product, right? So again, 3D printing is an additive manufacturing process. But there's also another one that some people may not always think of, and that's injection molding. So injection molding is also an additive process. There is some kind of mold, but then you add material, right? You shoot the plastic or whatever polymer or whatever material into the mold, and out comes a part. So these are the two kind of big processes when it comes to additive manufacturing. Again, we're focusing on 3D printing today, but there are a lot of parallels when it comes to injection molding. One of the advantages to the 3D printing industry is that it benefits from a lot of materials available in the injection molding process. Because the method of, or because the manufacturing method, although it looks different, in principle, right, it is kind of similar. You're heating up some kind of material, you're depositing it, and stuff like that. So 3D printing benefits a lot from injection molding, which is pretty cool. All right, so into more like nitty-gritty for 3D printing stuff, right? There's a bunch of different applications for 3D printing. Applications are growing every day with people finding new ways to apply 3D printing, or inventing some kind of 3D printing technology to apply it in different applications, right? So most people think of 3D printing as a very good rapid prototyping tool, which it is. The advantage for 3D printing is that it's a lot more inexpensive compared to other methods, right? If you're going to injection mold something, you're going to have to dish out a really large sum of money to create a mold. Then you're going to have to get an expensive injection molding machine or have some service do it for you. And then if you make a mistake in the mold, you're going to have to remake the mold. It's going to be expensive, and it's hard to iterate, right? Or it can be expensive to iterate. So the advantage of 3D printing is that you don't need any tooling, right? The 3D printer is good to go right once you build it. You just press print, it makes your part. You can do very complex geometry with a very low cost. So that's why 3D printing is pretty cool. And it's those kinds of advantages are finding its ways into more and more areas. So they're using 3D printing for automotive applications, sometimes not on a super wide scale, but for some very specialized things like race cars and stuff, 3D printing is becoming more and more popular. Again, because you can get really crazy geometries out of it for relatively low cost. It's becoming more of a go-to for some applications, especially when weight is a concern, right? So aerospace, automotive, all of those benefit from 3D printing. People are also 3D printing houses, which is pretty cool, and they're even doing like bioprinting. I think there's some like 3D printers in space that make like pizza or like pancakes or something like that. It's pretty interesting stuff. But yeah, there's almost limitless applications to 3D printing. Like, people print jewelry, or at least they might print like some kind of mold for jewelry with 3D printing. So yeah, there's a lot of cool stuff happening. Obviously, there's more than one type of 3D printing. So, a lot of us think of FDM 3D printing, which I'll touch up on in a little bit. But there's a couple other 3D printing types that you can kind of learn more about. So, one of the more industrial ones is what we call SLS, or selective laser sintering. And basically, instead of a filament, you have some kind of powder with a polymer, right? So, oftentimes it's like nylon or something like that. It's a very fine nylon powder. They'll use some kind of laser to melt a very small layer of that material, and then they'll cover it with more powder, and they'll shoot more lasers, and they'll do it over and over again until you have your completed part. So SLS printing is pretty cool, but for us, it's a little bit out of scope for, most consumer uses, just because it's an SLS setup is pretty expensive. But you can get like SLS services, and their parts are pretty strong. There's also SLM, which is not on this slide, but it's the same thing, but with powdered metal. So SLM is selective laser metal. So you can get like metal 3D printed parts, which is pretty awesome. If you're in like the 3D printing space, especially like the high speed 3D printers, some people are using SLM to 3D print their tool heads, right? So they get really high amounts of rigidity, but also low weight because they can precisely control the geometry for a relatively low cost. So SLM is pretty great. Again, it can get kind of expensive. I know I said low cost, but you're still dishing out maybe a couple $100. So yeah, it's pretty cool though. The other one on this slide is SLA printing. It's similar to SLS, but instead of a powder, you're using a resin. So it's a liquid material that you shoot a UV light. So there's basically a TV or a display at the bottom that shines UV light in a very specified area. It'll partially cure the resin. It'll move up, it'll expose it again, and it'll do it over and over again until you have your final part, right? Then you have to clean it and then cure it more with more UV light, and then you have your final product. So SLA is also pretty cool. It's become pretty accessible for most people, but there's a little bit more prep involved. You need to make sure you're printing this in a very clean area, a very well ventilated area, but it's really good for highly detailed models. So if you play D&D or like miniatures and stuff, SLA is a very good avenue for that because you can get a really high level of resolution in a very small area. But the main one that we're going to be talking about today is FDM 3D printing or FFF 3D printing. So I might use FDM and FFF interchangeably. They both basically mean the same thing, except FDM is, I believe, a trademark name. So I think Stratasys has like a trademark on the name or the term FDM. So a lot of other companies will use FFF instead, but they both mean the same thing, or essentially the same thing. So a lot of you may be familiar, but I'm just going to review this. If you're wondering what FDM or FFF printing is, it's basically a fancy hot glue gun with a robot on it. But instead of hot glue, you're using some kind of polymer and extruding it out of a nozzle, right? So you can see in this diagram here, there's a lot of blue. This blue filament comes in the top. It has some kind of extruder, these little wheels here, to push it into a heated nozzle. And then using precise control, you can control this motor and the position of the nozzle, and it moves around a bed and 3D prints your object, right? So it deposits material very precisely, and then in layers until you have a fully 3D printed part. So that's mainly what we're going to be going over today. FDM printing is really awesome. Again, I am a huge nerd for 3D printing. At this point, I have like 9 3D printers, so it's like kind of a problem. I have kind of a problem, but I love it. 3D printing is really fun. So yes. Okay. Obviously, every manufacturing process has some kind of limitation. And although FDM 3D printing has very little restrictions, there are things that we kind of want to keep in mind when we make stuff. I'll get to that later. I forgot about this slide. Okay. But yeah, there's a bunch of different settings when it comes to 3D printing, right? So if you think about your normal 2D printer, you have a kind of limited amount of settings when it comes to how you're going to print stuff, right? You can change like DPI or like scale and stuff like that. But when it comes to 3D printing physical objects, there's a bunch of other parameters that you need to keep in mind. So the first one is layer height, and that's just kind of the vertical resolution of your part, right? So how 3D printers typically work, or how FDM printers typically work, is they take your 3D model, it gets cut up into a bunch of thin layers, and then the printer will print one layer, it'll move up, it'll print another layer, and it'll do it over and over again, right? So specifying your layer height will specify, how fine you want your vertical resolution to be. You can see here on the left with 0.8 millimeters, you can visibly see these layer lines here, right? It's a lot more, it's very coarse, but then as you go farther right on this example print, you can see the layer lines becoming less and less visible, right? And it's because each time it changes layer heights, it becomes a lot more fine, to the point where at 0.1 millimeters it's very hard to see, right? So there's advantage and disadvantages to picking any of these layer heights, right? The main advantage to a very tall layer height like 0.8 is that your printer is going to print a lot faster, right? Because, it has to print less layers, that's just less time, right? So, assuming this is a cube, right? Let's say this cube needs 100 layers, and each layer takes 20 seconds, right? That's a okay amount of time if you're doing, 100 layers. But if you're doing like 300 layers, then, that's going to triple your time, assuming, the geometry is the same for each layer. But so again, increasing that layer height typically makes the part finish faster. And one of the other advantages, which is kind of like a nitty-gritty thing, is that the part might be stronger at a large layer height. So the reason for that is a lot of 3D printed parts fail on the layer lines, right? So the bond between each layer won't be as strong as, the bond of the material itself. So it typically fails on a layer line. So because of that, if you have less layer lines, you technically have, less points of failure compared to a print with many, many layer lines. So if you're looking for strength, sometimes increasing your layer height can actually make your part stronger. But there are other ways of doing it as well. Perimeters, in my opinion, is one of the best ways to increase your to increase your strength, while not sacrificing too much speed, right? Typically, I print with a layer height of 0.2 millimeters, so kind of in between these two here, and that in my experience has been a pretty nice balance between like visual quality, right? You can kind of not see anything here, but also speed, right? If you go to 0.1, prints take quite a long time, but if you go too far to this way, you can start to see the layer lines. In some cases, it doesn't really matter, but if you want things to be nice and pretty, 0.2 is typically where people go. Anyways, back to perimeters. If you didn't know, most 3D printed parts are hollow to some extent, right? So the inside of the print has, is full of air. There's usually some kind of pattern on the inside to give it some rigidity, but most of the strength comes from the outer surface, right? And to make your part stronger, you can make the outer wall a little bit thicker. So typically, for very low strength parts or just like parts that you might leave on your desk, people like to use, anywhere between like 2 and 3 perimeters. That's typically the norm, right? So you can see here in this image, you can see these 2 yellow lines here. That's like 2 perimeters. But, as you go farther and farther to the right, you can see there's more and more perimeters. So, increasing your perimeters makes your prints a lot stronger, just because the outside is a lot more rigid. And I found that increasing your perimeters before you increase your infill will actually make the part stronger, like especially when it comes like to strength to weight ratio. So you can increase the infill, which we'll talk about in a little bit, but increasing your perimeters is typically more effective for the weight and also the time, right? You just have to do one more loop around instead of increasing the whole density of the part. So that's typically pretty good. Obviously, you're not going to do like 0% infill for everything, but there's a nice balance. So for me, when I print more structural parts, I typically do like 4 perimeters and 25% infill. And then for more chill stuff, I might do like 2 or 3 perimeters at like 15 to 20% infill. So, yeah. Again, it's a balance here, so if you increase the perimeters, it gets stronger, but obviously it takes more time, just because there's just physically more material that you need to lay down for every layer. So, if you're printing something that's on your desk that's not going to be under significant load and you want it quickly, reducing the perimeters might make you get your part faster. You might save a little money because it's just less material. But yeah. Okay, yeah. So I talked about infill very briefly in the last slide, but again, 3D printed parts are typically hollow inside. So you can control the density of your part on the inside by changing the infill percentage. So, 0% infill is just like a completely hollow part, and then 100% infill is a completely solid part. So finding a balance somewhere in the middle is typically what people like to find. For most people, 10 to 15% infill usually satisfies their needs. But for more, strength-related parts, something might be under a good amount of stress, you might want to increase that infill. Again, pairing it with increasing perimeters typically results in pretty good typically ends up with pretty good results when you pair both of them. I find, perimeters gives you a lot of the strength, but increasing that infill a little bit will kind of help as well. Obviously, increasing infill increases cost and print time because it's just more material to lay down. But, all of this is kind of a give and take. All right, so supports. So sometimes when you create a 3D printed part, or when you design a part and you send it to 3D printing, you'll kind of be put in a scenario where the geometry is quote-unquote impossible, right? So unfortunately, 3D printers are subject to the laws of physics. In this case, gravity is a very big one here. So you can't really print things in midair, right? So you can see this geometry has this cylindrical shape sticking out the side. And if you were to try to 3D print it with just nothing but the geometry, your printer will try to print this. It'll move the tool head out, but because it's molten plastic, it'll droop and then fail. I think failed prints is something people typically want to avoid. So one way to avoid that is by adding some kind of sacrificial material, right? So you can see here in this image, there are these kind of gray lines here, or in the image on the right, you can see that kind of bluish purple material underneath this part. So supports just kind of are some kind of sacrificial material that you can use to make sure your print completes the geometry that it's looking for. But then at the end, because it's not supposed to be there, you have to remove it. So once you take it off the 3D printer, you have to remove the supports, and then you can call it a day. Obviously, adding supports to a 3D printed part increases cost and print time, just because you're adding more material into your print. Obviously, for some geometries it's necessary, but because you are in a Fusion 360 course, you're the designer. So when we talk about designing for manufacturing, this is one of the things that we like to highlight, right? So because you're the designer, you have the ability to design some of the supports out of your part. And what I mean is, you might be able to tweak your geometry or change your part in a certain way where it doesn't need supports to still function the way you want it to. Maybe in this case, the geometry had to specifically be that way, and that's why this person used supports. But in general, because you're designing parts, you can kind of do your best to make sure supports aren't needed. The big plus for designing supports out of your print is that there's zero post-processing, right? A lot of people really like to 3D print something, just take it off the printer once it's finished, and then throw it on to whatever they're using it for. People don't really like to deal with removing supports. They might need pliers that might stick to your part. It might make your surface finish kind of poor. So in general, if you can avoid using supports, I definitely would. Again, there are specific scenarios where you're going to need it, and that's okay. But at least having this in your mind to try to think about your part and be like, hey, do I really need supports here? Can I design this another way to make sure I don't need it? It'll save you money because there's less material to print, and it can save you time. So especially if you're printing, very large volumes of parts, right? It might take you 5 minutes for one part. But if you're doing 1,000 parts, that's a lot of minutes to kind of post-process stuff. So that's why we like avoiding to use supports. All right, yeah. So this slide shows an example here of supports. You can see, this H here has this supporting filament to prevent this H from drooping. You can see the T here also has stuff to support it. There's a couple of things that the user could have done to avoid supports. In some cases, I'll talk about bridging in a little bit, for short distances, printing supports could be unnecessary. So for short distances, I think it's on it's a later slide, but basically, your printer can quote unquote print in midair if it's a very short distance. If you have good cooling, it won't droop too much. But as it gets longer and longer, bridging becomes more difficult. For the T here, there's kind of nothing supporting on this left or right side, so having the supports there is probably necessary to prevent the T from drooping. But there's another way that you could have avoided supports on both of these without bridging or anything. I guess this is a good time to be a little interactive. But does anyone have any idea or recommendation for, this user to print these parts without the need for supports? Feel free to put it in the chat or unmute yourself.
So you just lay them down flat?
Yes, so that's a very good recommendation. If I was this person, I would probably lay the H and the T down flat, or even the V for that in that case, right? So print orientation is one way you can remove the need for supports. So when you're designing your parts, you might want to think about what face is going to be on the print bed, right? So you can optimize for minimal supports, right, by printing it flat. But you can also optimize for strength. So, if in this case, for whatever reason, like this user really wanted these letters to be strong in like the vertical direction, or I guess like the horizontal direction, to prevent it from like shearing like in half. Printing it vertically may have been the right move, but if they printed it in this way and then someone applied a force at the bottom of the T going like horizontally, like let's say the T was upside down, right, and you're pressing on this, it could snap like right here at the transition between this top part and the vertical part because it's printed on these layer lines, right? It could snap right here. So depending on what you're going for, if you laid the print down, the layer lines would be oriented in a way that the T would be much stronger, and for that case, the H as well. So keeping in mind print orientation, that's something to consider as well. So in an ideal scenario, you consider both print orientation and geometry. So you have, minimal to zero supports, but also the strongest part. Okay, someone asked, how are supports exactly 3D printed? Does it also have a surface finish or other things like that? So, I mean, supports are 3D printed just like any other component. They're just kind of automatically generated with the software that you use to generate the instructions for the printer, right? So you can see this T here has this like random material on the left and right. Those are supports, and they're printed layer by layer, just like all these other components, or just like all the other parts of your model. Does that make sense? If you're wondering about surface finish, like it kind of varies. Most of the time we don't really care about surface finish for supports because you just remove them and like throw them away. But there's different styles of supports, which I can show you all later. This is a very like standard support, but there's also like organic supports that look like little trees, and that's kind of there to like minimize material waste and stuff like that.
Are these like all part of like the printer settings? You don't have to like put supports in your actual like Fusion design, do you?
Yeah, so that's a good question. In general, like these supports are like automatically generated when you 3D print your model. So we're going to be slicing parts today, which is like preparing your parts for 3D printing. I'll show you how to turn it on, right? So you're not going to have to manually model these supports, though in some specific scenarios, people will manually model supports because it might optimize the part for like minimal material waste, but that's a very edge case scenario. Yeah. Did that answer your question?
Yeah. Thank
Okay,
you.
cool. Okay, so I was just talking about slicing and stuff like that, so that's kind of a perfect segue because we're going to be slicing components now. So basically, we're going to install a slicer real quick, and then I'm going to teach you how to prepare your model and slice it for 3D printing. So essentially, what a slicer is, right? You know Fusion now. what you do is you export your 3D model from Fusion, or you download a 3D model off the internet, and then you run it through a program called a slicer that converts your 3D model into a very long list of instructions for your 3D printer. All right, so I've been talking about slicing. Again, it's because it takes your 3D model, it slices it up into a bunch of 2D profiles, and then using those profiles, it'll create some kind of toolpath for your 3D printer to follow. So there's a bunch of slicers out there. Today we're going to be using Prusa Slicer, but there's Kira, Bamboo Studio, Orca Slicer, Simplify 3D. There's a bunch of wow, I can't talk. There's a bunch of different slicers out there. Many of them are based off each other, or they take inspiration from each other whenever a new feature comes out. So they all essentially do the same thing. Some of them might be better for certain scenarios, but in general, they basically work the same. So today we're going to be using Prusa Slicer, but if you use this one, you're probably going to be able to use the other ones. Similar to Fusion and like SolidWorks, right? They basically do the same thing. The buttons are in different places, but the general workflow is the same. So everyone's going to want to download Fusion. So if you go under resources, there's this download link. You want to download Prusa Slicer. Should work for any operating system you're running right now. You should have a Windows or a Mac. But I'll give everyone a little bit of time to download this. Is anyone having trouble accessing Prusa Slicer? Oh, I need to change this. Let me fix this real quick. This was an older Prusa printer, so this slide is slightly outdated. Oops. Okay. Who needs more time to install Prusa Slicer? Okay, someone raised their hand, so I'll give them a couple more minutes. I have two people with raised hands right now. I'm assuming they're still installing Prusa Slicer. When you're when it's installed, do you think you can maybe lower your hand just so I know it's good to move on? Oh, okay, there's a third hand. There's not a third hand.
Andrew, I have it downloaded, but how do I select like what printer I'm using?
Okay, I can go over that in just a second. Do you have like this welcome wizard open or did you close it?
I closed it.
Okay, so if you close like the welcome wizard, I've done it before. You just want to go under this printer drop down, and then you can go add and remove printers, and then add / remove presets. And it might take a while, but it'll kind of reopen this, and you can select your printer. And I'll go over that in like just a minute.
Okay, thank you.
Okay, so once this loads, I see no hands raised, so I'm gonna just move on and set all of this stuff up. Okay, so when you first open Prusa Slicer, you should be greeted with some kind of window like this. Again, if you didn't, or if you closed it on accident, I just ran through how you do that. You go into that printer thing and add, remove printers stuff. Okay, so you'll be greeted with this configuration wizard. It'll ask you if you want to log into your Prusa account. If you have one, you can. I do, but I'm just not going to right now. You can kind of click through this. This will just kind of select which printers are available for you to select. Or do some loading. But the main thing we're interested in is the Prusa FFF. Right? It's not FDM because FDM is trademarked. No, I don't want to install. Okay. Let's go. Okay. So when you get to this window here, we're going to make sure that we all select the same printer, right? Every printer has different dimensions or different speed capabilities and all that stuff. And one of your assignments, or the assignment for today, is to slice a 3D model, and I'm grading it based on the time. So when you finish slicing it, it'll display like a total print time. And if you're using a 3D printer or a different 3D printer than the one I have selected, you're going to get a different time. And if you get a different time, then you're going to lose points. So again, please select this printer. Some people decide not to, and then they lose points. But I'm telling you now, please do it. You want to make sure you select the Core 1L. So it's just this one. And you select the first nozzle, the high flow 0.4 millimeter nozzle. Again, if you select this and you slice everything correctly, you should be within 1 minute, or your print time, your displayed print time should be within 1 minute of mine when I do it, like right now. So again, please use this. Someone won't do it, and then you're going to lose points, and I'm going to be sad. Yeah, please do it. Once you've selected that, I mean, if you want, you can click through the next. You know, it'll kind of show you other things that you can select, right? There's like other Prusa printers, there's their SLA printers, and then there's also other printers, right? So if you have a printer from another manufacturer or another brand, you can typically add it here. Like for me, I have like a Voron Trident, which is somewhere here. Yeah, so I have like one of these printers. I could add it, but you know, I'm not going to. But once you've selected the correct printer, which should be the Core 1L with the high flow, 0.4 millimeter nozzle, you should press finish. It will close that dialog, and then you'll be greeted with this kind of workspace. So similar to Fusion, right? You have a very big area where most of your work is going to get done. Here you can kind of see the virtual build plate. So, you know, this is a virtual representation of your 3D printer. You know, if you print stuff or you try to print something that's bigger than this, it's not going to fit, obviously. So this is kind of what we're limited to, at least for this printer. In terms of navigation, the controls are a little bit different compared to Fusion. So if you hold the left click button, you can kind of orbit around. If you hold right click, you can kind of pan side to side, and then you can scroll to zoom in and out, which I guess is the same as Fusion. There's a bunch of settings, or there's a couple settings over here that you can change, and then there's more settings on the drop downs or tabs up here. So over here, you can see under print settings, if you click on it, there's a bunch of different parameters. You know, here it's specifying the layer height, right? So 0.1 is 0.1 millimeters, right? And then 0.28 is like a lot coarser. So this printer, at least for the standard settings, goes from 0.1 to 0.28. But you know, you can modify them and make it go beyond that. Anyways, you can change that here. You can also change the type of filament. You know, we're going to talk more about materials next week, but you know, there's a bunch of different material options for you to choose from. Please choose generic PETG for this assignment. Again, sometimes material choice will affect the print time, so please choose generic PETG. If you use a different material, the print might be faster or slower. So, you know, to avoid losing points, please use this. Printer, you know, should be the Core 1L with the high flow 0.4, like I've been saying. And then here you can enable or disable supports and also control the infill. So there are a couple of settings here. You know, these are probably the ones that one would change the most. But if you want to change more settings, you have to go under print settings, which is this tab up here next to platter. When you go into here, you know, you can change the layer height again in the same drop down here. But you have a little bit more, right? You can change the number of perimeters right here, you know, manually change layer height and stuff like that here, but I don't recommend it. And you can modify, you know, other parameters, right? Like top and bottom layers. The main thing that we're interested in here is perimeters, so we're going to be changing that. You know, you can also go under the infill settings to kind of get a more precise control of the infill that you're doing. You can change like the pattern of the infill, like how it looks like on the inside, you know, depending on your use case. Changing this might be optimal for strength or aesthetics. In our case, we're going to leave it as is, but we'll change the density. And then there's a couple other drop downs for other settings, right? If you want even more settings, which I guess isn't super relevant for this class, you can change the mode to like normal or expert. And you can see when you do that, you get a lot more stuff that you can kind of specify. But for now, beginner mode is just fine. Okay, so I'm going to go back to the platter, which is just over here. And I'm going to start adding models. So, you can't really 3D print anything if there's nothing to print. So we need to import some kind of file. So we could do that with Fusion, but in our case today, we're just going to download something and then slice that. So, oops. If we go back to the Discord, there's this link to printables with this cute little boat. This is the 3D Benchy. So if you don't know what this is, it's a pretty like iconic 3D printer test model. So a lot of people will print these as their first prints, or they'll print it for calibration. Basically, the idea behind the 3D Benchy is that it's in essence kind of a torture test for your machine, right? So there's a bunch of geometries on here specifically designed to be difficult to reproduce. So the philosophy is if you can print a really high quality Benchy, then it usually means that anything else that you try to print will also be pretty high quality. So I can point out some of the geometry once we import it, but we need to import it first. So if you go to the link, you want to scroll down and download the STL file. So under model files, there's this STL file. You want to download it, and then you want to import it into Prusa Slicer. So I'm going to do Control I, import the Benchy. You can also drag and drop. But now we have our Benchy in our build plate, right? You can kind of see the relative size to this printer. Can definitely fit a bunch of these, but we're just going to do one for now. For this assignment, I've specified a couple different parameters that we want to focus on. So obviously we're going to be using Prusa Slicer, that printer I specified. We want to change the perimeters to 3. So I'm going to just change this on purpose. So if we go under print settings and we change the perimeters from 2 to 3, that's what we're looking for. It also specifies that we want the layer height or resolution to be 0.15 millimeters on the speed profile. So if we go down here, there's the 0.15 speed profile. If you click on it, this pop-up will come up. It's basically saying, hey, you changed this parameter. Do you want to keep it, or do you want to discard it and modify it again later? So if you hit discard, it goes from 3 back to 2 because 2 is the default for this profile. So I'm going to change it back to 3. We need to specify the infill to be 20%. So I'm going to go under infill, change this to 20%. Again, leave the pattern to just be grid. And then we want to turn supports on. So for support material, I'm going to auto-generate supports. And then I'm going to leave this unchecked. So when I go back, I've applied all the settings that I am looking to apply. So I'm ready to slice it. So if I hit slice now here in the bottom left, or I mean bottom right, your computer will slice the model, it'll think a little bit, and then it'll give you a preview of your part or of your model. So you can see here, all this green stuff was automatically generated, right? It's an auto-generated support. But you can kind of see what the model is going to look like once you finish the print. Typically for a benchy, you're not going to be printing it with supports because the whole point of this print is for it to be a torture test without supports. But I'm just turning them on for this assignment just so you know how to use it. So once you slice your model, you can kind of go through the preview with this vertical slider. You can go up and down to kind of preview every layer. So you can see at the start, the first layer looks like this. If I use the horizontal slider, you can even see every single movement that the printer is going to do. If you look here on the left side, you can see all these like letters and numbers. This is the G code that your 3D printer is going to read, right? So it's basically a very long set of instructions and movement positions that your 3D printer is going to follow to recreate your part, right? So you can see as I scroll through it, it goes line by line and creates the first layer, right? Fills in the perimeters, fills in that infill, and then it's finished, right? Then it goes up one layer, and then does it again, and then it'll continue to do that all the way until your part is finished, right? The preview is also useful because you can see the infill here, right? The inside's hollow. And yeah, it's pretty cool. I'm going to turn supports off to give you a better visualization of the benchy. You'll also notice that whenever I turn things off or I change some kind of parameter, the preview is going to change and it's going to ask me to slice now again. So every time you make a change, you're going to have to reslice because it has to recompute. It has to recompute the G-code file. But if you look around on the benchy, you can see there's a couple areas where the print might be difficult to reproduce. One big one here is if you look from the side, the angle of this hull is pretty steep. And, we'll talk about overhangs in a little bit, but, this kind of geometry could be difficult for a 3D printer to reproduce. Same with like the little holes here in the hull. You can see those areas are overhangs. Same with the top of this window here. This window is a little bridge that goes across. So it's a lot of little things, right? The writing on the bottom, right? If you don't have a good first layer, this may not look good. There's even like a very tiny detail here on the back. So all of these things kind of point towards, or all of these things are like little parts that make this print difficult. And if your printer can handle it, then you'll print pretty awesome stuff. I think now is a good time to go over 3D printer limitations because that might help put some of the geometry of the benchy into perspective. All right, 3D printing limitations. So, I just mentioned overhangs, right? So basically, when you're 3D printing stuff, you can't print things in midair, right? That's why I was talking about supports earlier. But there is a certain threshold that you can kind of print before needing supports, right? So you can see here, on the left, this sloping angle is not very aggressive. It's pretty shallow in relation to this wall right here. So it's a lot easier for a 3D printer to reproduce this geometry. But as this geometry kind of pulls out wider and wider, it gets more and more difficult to reproduce. So as you go farther and farther, eventually you'll hit 90 degrees, and that's when it's, completely sideways, and you'll definitely need supports. But there's a sweet spot kind of in the middle where you can have some geometry jutting outwards while not needing supports. So typically the rule of thumb here is 45 degrees, and it's halfway between 0 and 90 degrees, so it's a nice middle ground. One of the nice things is like you can add a chamfer on your bottom of your prints, and it requires 0 supports, right? Because most chamfers are usually 45 degrees, so 45 is okay. Sometimes you can go a little bit higher. You can go like 50 or maybe even 60 degrees, but that's starting to push it. It definitely depends on the printer you have, and sometimes even the material that you're printing, right? If you have a really nice dialed machine, you might be able to be a little bit more aggressive on the overhangs. But in general, people typically stick or try to stick to a nice 45-degree angle. It's nice and even. But again, if you need to go more than that, a little bit more might be okay. But if you go too far, you're probably going to need supports. So if you really want to get really specific about why, it has a lot to do with how the layers overlap, or how the printer does the perimeters. So if we zoom in really, really closely, you can see the individual layer lines and the individual perimeters. But you can see near the top of the hull, each edge of the perimeter is not jutting out very far compared to the previous one, right? So the previous layer is kind of supporting the layer above it to prevent it from drooping. But near the bottom of the benchy, you can see the slope is a lot steeper. It's really prevalent on this first layer, right? You can see here, this first layer ends right here, but the next perimeter extends all the way out here. And if we even look at it from this angle, we have this perimeter here, but right on top of it, you can see when they print this perimeter, come on, you can see here that there's almost nothing supporting this perimeter out here, right? And it's because that geometry is so aggressive. So this is the kind of stuff that we're trying to avoid. Obviously, for a torture test, you're trying to push the limits of the printer and see how it does. So, if your printer wasn't dialed in enough, you might have some kind of curling or drooping, at a point like this. So, as a designer, you can make it so you're not even putting the printer in these kinds of scenarios. But, if you have to put it in that scenario, a well-tuned printer will give you a higher chance of success. So overhangs are relevant in the hull right here, but it's also relevant for these curved or these holes, right? So if you think about it, the top of these holes are also their own overhang. All right, let me try to go straight on. You can see as it's printing, the bottom layers are totally fine, right? They're completely supported by everything underneath it, but as the hole gets taller and taller, there's an increasing amount of overhang, right? All the way to the point where this last layer for the hole is just completely straight across with nothing supporting it underneath, right? So for small holes, if your printer is dialed in well, you may not need supports. So, you know, here you're probably fine. But if you're printing really, really large diameter holes, you know, there's going to be more and more layers with a lot of overhang, and that's when you might want to consider adding supports. So that's an example of overhangs. If you go even farther up here, right, this arch is another overhang, right? So again, torture test. This is the kind of stuff that we typically, as designers, try to avoid. Obviously, if your printer or if your model needs this kind of geometry, you know, do it, right? We want this arch on this boat, you know, just because. So it looks like that. But if you can design out these overhangs, it might be beneficial for your printer. So there's a couple ways you could do it, right? I mean, you could just not have that geometry at all, or you can add little small features to kind of compensate. So again, I was just pointing out that hole on the hull, right? The last layer here is a nice overhang, and the slicer will represent overhangs in this blue color. You can see in this image, right, this hole was printed vertically, and the top of it is a little bit flat compared to the bottom, right? It's not completely round, and in some cases that's not ideal, right? You want a nice round hole. If you're putting a bolt through it, it might be hard to put through just because there's extra material in the way. So one of the ways that people combat this is by modifying the hole geometry to be a teardrop shape instead of just a circle, right? And this is very beneficial for the 3D printer because it eliminates the really steep overhangs on the top of the hole, right? Again, if we go back to this, a 45-degree angle is perfectly manageable for a 3D printer. So if you combine, you know, this 45-degree angle at the top of the circle, you essentially have 0 steep overhangs, right? It's just 45 all the way up to the top. So that prevents kind of the drooping and, you know, this kind of flat scenario. And in many cases, that's perfectly fine, right? You don't need your hole, or in many cases, you don't need your hole to be perfectly round, right? You just want enough clearance for you to put, you know, a bolt through it without having to kind of screw through the plastic, which you might have to do here if your tolerances aren't correct. So you can add these teardrops in your models to make it easier to print, right? So you can do it with holes, but you can also do it with like arches, right? So for example, if you wanted to make the benchy easier to print, you might want to modify this to have a more tapered top instead of a round top. So as a designer, you know, you can kind of design these out depending on your model. All right, bridging. So bridging is the next point. I mentioned it briefly. Here's a good example of a bridge, right? 3D printers can span short distances in midair, especially if you have good cooling. So, you know, the benchy is designed to have this kind of straight section for like this front window area, and it's intended to be printed without supports, right? So if you have a really well-tuned in printer, you can bridge across these short distances without it drooping too much, right? But the key, the key point here is that it's a short distance, right? As it gets longer and longer, the molten plastic, you know, doesn't really retain its structure as well. So you can see here the bottom bridge is okay, but as you go longer and longer, there's more filament that starts to droop, right? So then you're kind of running into surface imperfections, right? You're not really intending for the geometry to droop like that. And that's when you might want to start considering having some support material underneath to prevent that drooping, right? So your printer can reproduce, or typically reproduce, some short bridges, but try not to go super long, right? I've said this many times, but there was someone in a previous session, I was talking about how you shouldn't do bridges or long bridges, and then they sent me the Golden Gate Bridge for their final model. They designed it very well, it looked really good, but because it was literally a bridge, it made it very, very difficult to print. And when we tried printing it, we tried multiple times, it would just kind of disintegrate when we took it off the print bed. And that made us kind of sad. We didn't, we felt kind of bad just handing him a pile of filament when we returned the model. So, I encourage you to try not to do this too much, or if you have to, I can put supports, but try to avoid bridging if you can, right? Again, you're the designer of your final, so you can design overhangs and bridges out where possible. So, yeah. Again, short bridges, right, on this benchy is perfectly okay, but when it's getting longer and longer, it gets a little bit harder to reproduce without supports. Okay, so here's some more, a little bit nitty-gritty information for you when it comes to thermal expansion and tolerance. Basically, the process of 3D printing generates a lot of heat, right? And with heat comes expansion. So when you heat a material up, right, things tend to expand, and then when they cool down, they tend to shrink. So depending on the material, some materials are more prone to expanding and contracting more, but sometimes it can lead to print defects. So if you have a really large part, for example, if you have a very large footprint on the bed, as the print cools, the bottom will contract or shrink while the top is still warm while you're printing. And when that happens, there are some cases where the force of the shrinkage is so strong that it can start peeling at the corners, right? So in this photo here, you can see the corner here. I'm assuming it's not intended for it to curl up like that, but it can. So depending on the material, some materials are a little bit more prone to warping, but this is definitely something that can happen. So sometimes it's the model, sometimes it's the material, sometimes it's both, or sometimes it's the user of the printer, not cleaning the bed. So if you ever talk to someone who 3D prints a lot, they might complain, it's like, oh, the bed wasn't clean and then the part fell off. So sometimes some kind of warpage or something happens before the part falls off, and then you get sad because you wasted a print and some time. So, keeping this in mind, there's a couple ways of combating warping. One of the ways you can do it is by reducing the stress concentrations, right? So for parts like this, the stress will concentrate themselves at the corners. So that's why, this model kind of curled where it did, right? It's not going to curl, it typically doesn't curl in the middle. It'll curl on one of the edges, right? Typically corners. So what you can do is you can add fillets on these edges here to kind of round the corners, and then that helps spread the load across the whole radius instead of one exact point. So that helps reduce it helps reduce the stress concentration in the corners, and that gives you a little bit better chances for it to not warp. Again, it's a very nitty-gritty detail, but sometimes you might encounter situations and you're like, why is my print warping? You might want to try rounding corners if that's possible for your geometry. Another thing, oops, that's a little bit less of an issue now just because printers are typically tuned a lot better, is elephant's foot. Basically, if you've seen the foot of an elephant, you know, they're pretty long, but then the bottom is a little bit wider than the leg part, right? So when we call elephant's foot, wow, I really can't talk today. Elephant's foot in 3D printing is kind of the same thing, right? So you see here in this little kind of circle image, the bottom of the print kind of flares out from this wall. And typically, for most 3D printed parts, or at least the ones that I've printed, a lot of the walls are intended to be completely straight, right? You can see these two like kind of dark lines here that kind of represent where the geometry was supposed to be, and then you can see how it extends a little bit beyond that. And sometimes this is not what we want. Well, obviously, you know, this geometry, this extra geometry or material sticking out was not intended to be there. But sometimes it can affect how your parts interface with each other, right? If you're designing something with pretty tight tolerances and what this part is wider at the base than you intended, then it may not fit together properly. And, you know, that's not good. So one of the things I do to reduce the chances of elephant's foot being an issue is by chamfering most of my bottom faces, right? So if you chamfer the bottom face, it'll kind of cut this bottom at a 45-degree angle. And when you do so, even if you have elephant's foot and the material oozes out a little bit, it'll still be underneath the wall or the face of the wall that you're printing, right? If you're wondering how elephant's foot happens, it's typically because the way the printer is set up, a lot of people like to squish their first layer a little bit. So they'll kind of make the printer print a little bit lower than it's intended to, just so the printer has good bed adhesion, right? If the nozzle is too high, then the print is at risk of being too loose and then falling off. So people will print their first layers a little bit lower than what they're supposed to be, and then they'll kind of, the extra plastic will squish out. So, you know, if your printer is set up that way, you might want to add chamfers on the ends of your edges to prevent elephant's foot from being an issue. You'll notice that I specified that it should be a chamfer instead of a fillet, right? And that's because if you think about it, a fillet is an overhang, right? So if we go, let's say, if we filleted this edge, it'll look almost like this, right? And the bottom part of the fillet would be a very, very large overhang. So for bottom faces, I highly recommend you use chamfers because they're just a straight 45-degree angle, right? But then for all the other faces, right, like these edges here, fillets are perfectly okay. And in some cases, they're preferred because it'll spread that stress concentration along the corners. So knowing where to put fillets and chamfers is definitely, you know, something that you should keep in mind. And that's knowing your print orientation when you're modeling something will help you determine whether an edge should get a fillet or a chamfer. I hope that makes sense. Yes? Okay. The last thing on this slide is print tolerances, right? Nothing is ever the perfect size that you're looking to have, right? There's always some kind of tolerance the part might be a little bit bigger or a little bit smaller, right? And this doesn't just happen for 3D printing. It happens for all the other manufacturing processes as well. And when you're modeling things, there will be scenarios where you model things to interact with other things, right? Whether it be bolts, hardware, or other printed parts. You want to make sure you have some kind of leeway or tolerance designed into your model. So typically, I like to think that a 3D printer's tolerance is around like plus or minus 0.2 to 0.4 millimeters, right? So that means, if I print a part, there's a chance that it might be slightly oversized or slightly undersized. So you need to account for that when you're modeling things, especially when you're interfacing with other things, right? So if we go to this hole, for example, let's say I want to put an M3 bolt through it, right? So the nominal diameter for an M3 bolt is 3 millimeters. But when I model this, I'm not going to make it exactly 3 millimeters. I want a little bit of extra space. So for me, I like to do like 3.2 millimeters or 3.3 if I want it to be a little bit looser. But it's a little bit more than the specified nominal diameter. And it's a good idea to do that with parts that interface with each other, right? If you have, one piece that goes inside another one, I'm going to make that piece, or either one piece or either the piece that goes inside a little bit smaller, or the piece that is outside a little bit bigger, right? And if you don't do that, you might encounter a challenge like this. This is another previous final for this class. Someone made this kind of, Lego-like figure, but the issue is the studs for the torso did not fit into the body completely, right? So it's either because the body was made a little bit too small or the torso was made a little bit too big, right? So, if they were modeling this, they might want to undersize the pegs or the studs on the legs a little bit just to make sure the whole torso would slide on more easily. So this is a good example of keeping tolerancing in mind. If you have any questions about tolerancing, feel free to ask me either now or when you're designing your finals. I'm always happy to give feedback on your designs. So yeah. I want all your finals to be as successful as possible. So, if you have some concern, I've had people reach out to me like, hey, is this too small? Or are these tolerances okay? I'm happy to let you know because I want your finals to work well. Any questions about, warping or anything like that? No? All right, cool. But yeah, that basically sums up today. I know it was a lot of talking, so I hope you're still awake because there is a quiz associated with all the things I've been talking about today. So in, the course material section, there's a quiz. So you're welcome to take that now or take it later. But it mostly just covers all the 3D printing stuff that we talked about today. But if you're worried that you maybe weren't paying attention or you missed something, I am recording this lecture, so you can watch that later. But you also have infinite attempts on this quiz. So again, don't worry too much about your score, right? The main objective for you is to come out of this class learning something. So, if you take this quiz, you don't do super well, you can take it again and, get full points. But, the goal is just for you to understand these things. So, yeah. Okay, someone asked when the final project is due and where you submit it. The final project will be due 1 week after, like week 5. So next week is week 5, where we're going to be going over, some finishing touches for your final project. After that is class finishes, you're going to have 1 week to turn everything in. So I'll just make it due at midnight, I guess midnight Eastern time. So it'll be due the midnight of the following Monday, which is not the 6th, but the 13th. So your final is due Monday the 13th at midnight. Any other questions?
What should we include in our screenshot submission for the benchy?
Oh, okay, good question. So the main thing I want to see in your screenshot, obviously the benchy should be in the frame, but the main thing I'm looking for is kind of the statistics here in the bottom right. So it'll tell me how much filament, and specifically the time. So the time is incorrect right now because I don't have all the settings loaded in. But I think it's like an hour 16 or an hour 15 is what you should be shooting for. Yeah, hour 16 in normal mode. So if your time is not an hour 16, you may have missed some parameter. So make sure you get that checked out. Make sure you're using, the correct printer and also the correct filament, which is generic PETG. But you should have the exact same time as mine. I think for some reason Mac users get an hour 15. So, if it's an hour 15 or an hour 16, it'll be full credit. But yeah, that's the main thing I should see. If you screenshot like these parameters too, that might help me troubleshoot if you don't have the right time. But if you have the right time, then everything should be good. You can also screenshot this here as well, because that also has the time. And it even gives like the breakdown of where the time is spent on the top left. Did that answer your question?
Thank you.
Yeah, no problem. Any other questions? Well, if no one has any questions, we're basically done for the day, so we're finished a little bit early. If you have other questions, you're welcome to reach out to me later. But if not, I'll see everyone next week.